All right, this is the proof of the Pythagorean theorem using similar triangles. So here we were given a triangle ABC. The the uppercase letters represent the vertices of a triangle. The lowercase letters represent the lengths. So the length of CB is A, the length of AC is B, and the length of AB is C. I've redrawn it here. Okay, what I've added to it is I've added a line CD that is perpendicular to AB. Okay, so we have a line AB. There's going to be a point D on line AB such that when we make a segment CD, it's going to be perpendicular to AB. Okay, so we've included a line that's perpendicular. So the first thing we look at here is we notice we have three triangles. Okay, we have triangle ACD, triangle DCB, right? And then we have the big one, ABC. So we have three triangles here, the two small ones and then the large one. Okay, we also notice that those three triangles are right triangles. They all have right angles. And what we want to do is we want to redraw the two inside triangles, the two smaller triangles. And I'm going to draw them over here. Okay, so I'm going to redraw this small one. Okay, I'm going to flip it over, and then I'm going to rotate it. Okay, so we're going to have, here's D, a right angle. Here's A, and here is C. Okay. Right, and the distance between A and C was B. Right, the length of AC was B. Okay, now I'm going to draw the second. So let's stop there. Okay, let's stop there. Okay, we notice that these triangles have right angles. Okay, we know angle ADC is congruent to angle ACB. They're both right angles. We also know they share angle A. Okay, so we know angle A is congruent to angle A by the reflexive property. So we have two pair of angles, corresponding angles that are congruent. So we can use an angle-angle similarity to tell us that triangle ABC is similar to triangle ACD. If the triangles are similar, we know the sides are proportional. And if the sides are proportional, we can set up a proportion. So AD corresponds with AC. So we have AD. Let me do it down here. Okay, we have AD over AC. Okay, AD corresponds to AC. And then we know AC corresponds with AB. AC corresponds with AB. We know the length of AC is B. Okay, we know the length of AC is B. So we can put in AD, and we know the length of AD. Well, no, we know AC is B. Okay, and then we know AB is C. So we don't know AD. Okay. We know the distance. This represents the distance from A to C. We know that length is B. Okay, again, we have another AC. Okay, we know that one is B as well. Okay. AB, again, from our original triangle, AB is C. So AC is B, and AB is C. So we know AC is B, and then AB is C. From here, we can cross multiply. B times B is B. Oh, we'll just write B times B. And that's going to equal C times AD. Okay, B times B is B, B squared. So B squared equals C times AD. Okay. We want to hold on to this equation. I'm going to start and hold on to that equation. Okay, maybe even circle. Okay. So we have a B squared. Now we need to solve for or find what A squared might be. All right, so let's redraw our other triangle. So this triangle was triangle ADC. Now let's redraw triangle CDB. Okay, so our right angle's at D. Okay, so again, we are going to rotate it over. So flip it over and then rotate it down a little bit. So flip it over and then rotate it down a little bit. So here's D, here's C, here's B. Okay. We know angle D is a right angle. So we know angle ACB is congruent to, well, actually, let's, we know CB is A, and we know C, that's all we know there. Okay. So we know angle ACB is congruent to angle CDB, right? These are right angles, so right angle theorem, right? Right angle theorem. And this was reflexive property. Okay. We know we share angle B. So we know angle B is congruent to angle B, right? We're looking at these two triangles right now. So angle ACB was congruent to angle CDB. That was the right angle theorem, right? All right angles are congruent. And angle B is congruent to angle B because they're part of both triangles, so it's reflexive property. So reflexive property. Okay. Okay. So we know by angle-angle similarity, we have two pairs of congruent angles. So by angle-angle similarity, okay, we know that triangle ACB, ABC, is similar to triangle CBD. Okay, if we know the triangles are similar, we can set up a proportion because we know the sides are proportional. Okay. So CD, make sure I'm doing this right. CD, nope, let's go with BD, DB, BD, let's call it BD. BD corresponds with BC. And then BC, right? So BD corresponds with BC, and then BC corresponds with BA. We know that BD, we don't know the value of BD. We know BC though. Right? The length of BC is A. Okay. Again, the length of BC is A. So we substitute in an A. And then BA, we know BA is C. Okay. Right? So BC is A, so we can substitute an A here and an A here. And then BA is C, so we can substitute in A, C. Cross multiply. Okay, A times A equals C times BD. And again, this is a lowercase c. Okay, it represents the length Okay, so a times a is a squared. Then we get c times the length, side length BD. Okay. This is our other equation we want to highlight. Circle. Okay, is that outside of your camera length? Okay. So we cross multiplied. Here's our proportion. We substitute in our values from the original triangle. Cross multiplied. Okay, a squared c times BD. Okay. So I'm going to rewrite those equations up here. We have a squared. Let me get us back up top so you guys can see. So our first equation, a squared equals c times BD. Okay, and then we have b squared equals c times AD. Okay, I'm going to erase all of this. Okay. Erase all of this. Okay. I'm going to redraw this over here. So we have A, C, B, point D. This is B, so right angle, that's A. And this distance here, AB, right? AB is C. Okay. All right, so what we want to do, can we see all this? Yes. What do we want to do? Okay, we know this is what we're trying to prove. This is what we're trying to get. So we know A squared and we know B squared. So if we add these two equations together, okay, just like adding linear equations, all right, you can add x plus y equals 5 to 3x plus 4y equals 6. Okay, it's the same type of thing. We have two equations, add them together. We get a squared plus b squared, c times bd plus c times AD. Again, these are the uppercase BD and AD. They represent the vertices. Okay, maybe. Okay, and we know we need to make this equal c squared. Okay. So one thing we can do is we can, both these terms have a c, so we can factor out a c. Okay. Factor out a c. Right. It's like doing distributing in reverse. Okay. And then the last piece we need is we need to look at BD plus AD. So DB, or B, how's it written? BD plus AD, right? BD plus AD is going to equal AB, right? It's going to equal the whole thing. These two pieces added together give us AB. Okay, so instead of writing BD plus AD, we can write C times AB. And what do we know the length of AB is? We know the length of AB is C, right? The AD plus DB is C. Okay, the length of AB is C. So we know A squared plus B squared equals C times C. We know C times C is C squared. So for any right triangle, it doesn't matter what numbers, what values you have for A, B, and C, what numbers you put in there. Okay. As long as they are valid numbers for a right triangle, okay, we know if it's a right triangle, the two legs squared and added together is going to equal the hypotenuse squared. A squared, right? That's what we're trying to prove. So we've shown without a doubt using similar triangles that A squared plus B squared equals C squared. There's a whole website, and I told you guys there's over 100 different ways to prove the Pythagorean theorem. But right, thus we've proven the Pythagorean theorem. Okay, so we started with this. We created a perpendicular line, CD. which gave us 3 triangles. We found that those 3 triangles were similar triangles, which allowed us to set up proportions. Which allowed us to set up proportions. From those proportions, we could substitute in the values of AC, AB, or CB, A, B, and C. Okay, and then we could cross multiply, which gave us these 2 equations. Then when we added these 2 equations and did a little bit of algebra, we were able to determine that a squared plus b squared will always equal c squared. So I don't know. I think that's the best thing we've done, but judging by your reactions in class, it was the worst thing we've done. So we're a little bit at odds over that, but I think this is awesome. And only 16 minutes.